Assalamu alaikum all, good afternoon. My name is Shama Rashidi and I will be the moderator of today's session. On behalf of EAGE Local Chapter Kuwait board members, I'd like to welcome you to today's session. The title of this technical webinar is Leveraging the Power of Artificial Intelligence to Optimize Geoscience Workflows and Elevate Performance. It will be presented by our esteemed speakers, Mr. Kamran and Mr. Zubair. Mr. Kamran Laiq is principal geophysicist in Schlumberger, Kuwait. He works in North Kuwait Jurassic College and Master's Geophysics from Kuwait Exam University, Pakistan. He has more than 25 years of experience in G&G technical and management by working globally in various companies. He has extensive experience in exploration, appraisal, FD, and production, conventional and unconventional reservoirs. And the second presenter will be Mr. Zubair. Mr. Zubair is senior geophysicist in Schlumberger, Pakistan. He had Master of Geophysics and Master of Philosophy in Geophysics from Kuwait Exam University, Pakistan. He is an accomplished geoscientist with more than 10 years of experience in different disciplines, such as AI, machine learning solutions, structural, seismic interpretation, conducted training and workshops on latest technologies on different fields, such as data science, spatial modeling, machine learning, and velocity modeling. Our speakers will be delighted to share their knowledge and expertise with us. Now, kindly note that the session will be recorded and shared through our social media platforms. If you have any question or comments, we will have it at the end of the presentation at the Q&A session. You can also leave it in the chat box. Thank you all for attending. With this, I'd like to give the virtual floor to Mr. Kamran to start. The floor is all yours. Thank you.
My name is Kamran, as I've already been introduced. So good afternoon, everyone. Sorry for the little delay because of the internet issue. So I'll be presenting the topic. I'll be presenting the presentation. The topic of today's talk is leveraging the power of artificial intelligence to optimize geoscience, workflows and elevate performance. My other author on this paper or on this work is a very talented senior geophysicist and data scientist, Zubair, who is based in Schlumberger, Pakistan. So this artificial intelligence is not just the focus for the G&G industry, but globally, the whole world is moving, taking a quantum leap towards digital transformation. So it is an important subject for currently for all the industries as well. So the agenda for today's presentation is I'll firstly go through a basic overview, purpose, and what are the key objectives for this presentation. And then I'll start with the historical context of seismic interpretation, how it has evolved over the period of time, the current challenges and that the industry is facing, and the solutions by virtue of data science and artificial intelligence involvement. And then Zubair will take into more details, talk about more details about the data science and artificial intelligence theory and the workflows and its application in well log seismic interpretation by showing some worldwide analogs. In the end, why we need to integrate AI and expert knowledge. So we cannot degrade the expert knowledge. Obviously, these AI and machine learning solutions are there to improve the efficiency, but we still need the expert knowledge with it. And then in the end, finally, the closing thoughts. So now next slide, Zubair. Okay, so this slide gives you a quick snapshot of the overview, purpose, and the key objectives. So the first question that we ask ourselves, are the objectives the same today as they were 60 years ago? The answer is yes. The primary goal remains to identify hydrocarbon anomalies using structural and amplitude interpretation. However, the processes and the technologies, including computing power, has taken a quantum leap, especially in the last 5 years or so. So the key purpose of this change is to adapt to industry changes and new challenges by focusing on efficiency and precision, and of course, by maintaining its key objectives. The key objective of the artificial intelligence and machine learning based geoscience solutions aims to identify more subtle anomalies in complex structures combined with creativity, patience, and experience. Hence, the advances in processes and technologies have helped enhance accuracy of GNG analysis by emphasizing on efficiency and effectiveness, and eventually, better hydrocarbon reserves evaluation. This slide shows the historical context or the evolution in the seismic interpretation approach. So as you can see, starting from left, the process of well to seismic tie historically, represents it has always been a very crucial link between seismic and well data. But in the past, it involved a labor-intensive manual approach, starting with the digitization of well log curves supplied on paper. Subsequently, these digitized curves were processed to generate key outputs like check shot velocity logs or synthetic seismograms. Finally, these plots were attached to seismic paper section, allowing geoscientists to visually assess the alignment and correlation between the well and the seismic, enabling the identification of geological features and potential hydrocarbon reservoirs. Although this manual process was time consuming and intricate, yet it played a fundamental role in early seismic interpretation. However, in an effort to further streamline the seismic interpretation process, some companies started to digitize these hard copy interpretations and upload the resulting data to mainframe computers, as you can see on the extreme right hand side of the your presentation, for preparing computer-based contouring. This approach aimed to transition from manual, labor-intensive interpretation to a more efficient and computer-based workflows. However, notable drawback of this innovation was the limited interactivity. Once you upload the takes or the interpretation in the database, it was difficult to update, that data, because it was time consuming. So this basically restriction highlighted the need for more user friendly and interactive systems. So the introduction of early 3D visualization systems in the early 1990s, mark a significant advancement in the field of seismic interpretation. These systems, although groundbreaking, came with certain limitations again. They were often slow, expensive, and required a substantial shift in the mindset for interpreters. So, as we all know, the major structures have already been drilled globally, and now we are challenging, the modern exploration extends far beyond merely identifying large structures. Instead, the industry now pursues more subtle and intricate objectives. So today's seismic exploration endeavors to unveil complex geological features and reservoir characteristics, and furthermore, multidisciplinary integration, quantitative interpretation, and seismic analysis play a pivotal role. While the integration of artificial intelligence and machine learning solutions bring a new dimension to the industry. So this comprehensive data-driven approach now empowers geoscientists to uncover the intricate secrets of the subsurface, leading to more successful exploration and production efforts. So this slide gives you a quick snapshot of the challenges and the solutions that the challenges that the industry is facing, and what are the solutions by virtue of data science applications. So, as we are aware that the traditional seismic interpretation relies on domain expert who manually analyze seismic data, a process which is labor intensive, time consuming, and expensive as well. And geoscientists had to spend hours scrutinizing the data. Moreover, manual interpretation is also susceptible to biases and uncertainties. Interpreters may unconsciously introduce personal biases, which can affect the objectivity of the results. The other challenge is handling of vast data volumes. With the exponential growth in seismic data volumes due to technological advancements, Manual interpretation faces challenges in processing and analyzing these vast data sets within limited timeframes. So, conventional approaches struggle to efficiently utilize the massive amount of seismic data available, and which can basically delay the time decision making process. Uh, Lastly, but pretty importantly, we are also facing an expertise gap. The oil and gas industry often deals with complex nowadays and highly sophisticated problems, which requires deep understanding of various domains like geology, geophysics, engineering. So many projects, and moreover, many projects in this sector are experimental in nature because we are dealing with more complex issues. So which requires unique, and because of these unique challenges, we are creating an expertise gap, and it may be challenging to find individuals with the specific knowledge and skills required for these complex tasks. So, in order to address these challenges, the industry is increasingly turning to automated or semi-automated approaches in terms of data science, the application of artificial intelligence, uh, and these machine learning and artificial intelligence and advanced data analytics are being employed to enhance the speed and accuracy of seismic interpretation. These technologies can process large data sets more rapidly, reduce biases, which was one of the challenges, and assist experts in making more informed decisions. So the expertise or experience still making an impact, but you're reducing the time, reducing the biases, and making more informed decisions. They are enabling the industry to leverage the full potential of the extensive seismic data available around us and leading to better informed exploration and drilling decisions. So the next slide, please. So this is a question. So why data science and artificial intelligence are making up an impact in the oil industry to address these challenges. So the oil and gas industry, is no stranger to navigating economical and political cycles. However, the challenges brought about by the COVID-19 pandemic were unprecedented and had a profound impact on the industry. So the shift in the industry towards digital transformation happens primarily because of COVID-19, which led to this numerous shutdowns of the social activities, travel restrictions, lockdowns, which directly impact on energy consumption, sharp decline in global oil demands, and delays in exploration and production projects. So, and in response to this crisis, the oil and gas sector was forced to innovate and adapt to this new reality, which often involves reducing cost and maximize operational efficiency. And as a result of this, data science and AI based solutions gained significant traction in the industry as a critical tool to address these challenges. So, as part of one of the surveys conducted in 2021, digital transformation emerged as the leading investment priority for the oil and gas industry. So this marked a substantial change from 2019, when it was the third largest priority, and even more significant shift from 2014, when it was hardly funded. So this highlights the industry's recognition of the need to modernize and digitize its operations. The survey also identifies that the AI and machine learning and analytics as the top game-changing technologies in 2021. And then a large amount of oil and gas companies had plans to increase their investment in this sector. This shift toward digital transformation and the adoption of advanced technologies like MR, machine learning, artificial intelligence represents a strategic response to the industry's evolving challenges. So by investing in these technologies, oil and gas companies aim to enhance their competitiveness, optimize operations, and navigate the complexities of the energy market more effectively. This underscores the industry's commitment to embracing innovation and adapting rapidly to this global energy landscape. So this was a basic overview regarding the how what were the challenges, how we started as an industry, and then in order to address these challenges, the digital transformation. As part of digital transformation, machine learning and artificial intelligence started playing important roles, important role in the oil and gas sector, especially. So now I will hand over the presentation to my colleague Zubair, who will go into more details related to data science and artificial intelligence theory, and how these solutions have helped to elevate performance and optimize geoscience workflows. So it's over to you, Zubair.
Okay, thank you. So moving towards the core part of the presentation, that is data science and artificial intelligence, starting from data science. Data science is basically interdisciplinary field that serve as a catalyst for innovation and value creation. It's a multidisciplinary field that combines statistics, mathematics, computer science, and domain-specific knowledge as well. Through systematic analysis of data, data scientists uncover hidden patterns, trends, and insights that drive groundbreaking innovation. This synergy of diverse expertise empower organizations not only solve real-world challenges, but also identify opportunities for growth and value creation. The collaborative effort of data scientists in cross-functional team play a major role in translating raw data into fostering innovation, contributing to the overall success of business. For data science project, either the data is structured or unstructured, it's not a big deal. We need to analyze the past data as well. We can generate predictive insights and then define the strategic decision. On the other hand, AI is basically simulation of human intelligence in machine. Enable them to perform tasks that typically require human-like intelligence. It has a range of capabilities, including problem solving, rational decision making, and ability to behave like human. There are 5 central principles of AI. AI systems are capable of logical reasoning. They can acquire and utilize knowledge, plan and strategize, learn from data and adapt to changing conditions. And it's also involved natural language processing as well. One of the remarkable advantages of AI lies in its ability to handle complex tasks with remarkable efficiency. It facilitates the resolution of novel problems by leveraging the algorithm and data-driven insights, contributing to the innovation across various domains. AI not only augments computational capability, but also play a major role in overall understanding of data set, translating data from one form to another as well. So this is overall generic workflow of data science workspace. So it starts from collecting data from different sources. After data collection, the next step is to pre-process that data to ensure cleanliness. This crucial phase involves a task like handling missing value, removing outliers, and transform variables. Following data preparation, machine learning models are trained using the processed data, a process where algorithms learn pattern and relationship within the information. Evaluation of model performance is then carried out utilizing different metrics to assess the effectiveness of trained model. Successful models are then deployed for real-world applications that enable them to make prediction on new unseen data. The implementation of AI have 2 primary stages. One is training and the other is prediction. In training phase, models are exposed to data, allow them to learn pattern, relationship, and feature relevant to the task at the end. This involves optimizing the model parameter, to achieve the desired level of accuracy and performance. Once the model are trained, it moves to prediction phase, where it utilizes the learned knowledge to make informed decision or generate output based on new or unseen data. There are two major types of artificial intelligence. One is machine learning and the other is deep learning. In machine learning, algorithm and data collaborates to autonomously analyze information and make decision without direct human intervention. This application executes tasks independently, drawing on past experience to inform their action. It self-learn and perform tasks based on accumulated knowledge. On the other hand, deep learning, which is a type of machine learning and artificial intelligence, concentrating on the training of artificial neural network to execute tasks that traditionally require human-like intelligence. For its extraordinary achievement, deep learning has gained attention and popularity in recent times. Its success is attributed to the neural network with multiple layers to learn pattern and representation from the data. There are two methods that are commonly used in artificial intelligence. One is supervised learning and the other is unsupervised learning. In supervised learning, models are trained using labeled data, where each input in the data set is associated with corresponding target label. Learning process involves models studying pattern within the labeled data to make prediction or classification when presented to new data set. By comprehending the relationship between input feature and their corresponding labels, model gains the ability to generalize its knowledge and provide precise prediction based on the pattern. On the other hand, in unsupervised learning, models are trained on unlabeled data, meaning there are no explicit target label provided for input. In this paradigm, model objective is to autonomously learn pattern, identify cluster, and relationship within the data. The tasks that are usually associated with unsupervised learning, it's clustering, anomaly detection, and principal component analysis, where model identifies group or irregularities without prior guidance. The primary goal is to uncover hidden structure within the data. So now moving towards the main part of the presentation, what are the applications of AI in geoscience workflows? I will start with geological workflows, some of quickly, and then move to geophysical workflows, and at the end we will also see its application in reservoir modeling as well. So starting from geological workflows, interpreting wellbore data through log analysis can be approached as a supervised machine learning problem. The workflow initiates with the selection of representative wells from basin or field for training purpose. Ground truth interpretation are obtained from these wells, utilizing domain knowledge as well. Following this, a machine learning training step has been used, during which machine learning model is learned and stored in the memory. It's essential to choose a hyperparameter through manual tuning to optimize the model performance. In scenarios like where domain expert wishes to apply this machine learning workflow for log interpretation, they serve as both end user and domain expert as well. The final step involves testing or predicting where data from new wells not encountered during training are input into machine learning techniques for log interpretation and well-board data context. So error analysis, which is a crucial for evaluating model performance and limitation. Classification metrics help to identify where model makes error, misleading certain rock types. And for continuous properties, mean absolute error has been used that quantifies average absolute difference between predicted and actual values. It measures model accuracy in predicting continuous properties. So moving next to the well log inside here, I took the example of fishes interpretation and predictions to gain to gain geological connections. This contributes significantly by deeply understanding of our reservoir. To refine the model accuracy and effectiveness, the data set usually divided in two portions, training and validation. Model has been trained on one section and validated on unseen the other section. Usually data sets divided in 5 equal folds, and model undergoes 5 times of training and validation. For each step, one set is taken as validation and rest 4 are taken as for validation, for training. This approach not only diminishes data reliance on specific data subset, but also augments the model robustness, ensure a comprehensive and reliable prediction of well logs. By incorporating decision tree ensemble with voting and averaging for well log prediction, models become more robust and accurate and better suited to handle complex relationship of geological connections. This approach aligns with systematic data set division and cross-validation strategy as well. So moving towards the geophysical workflows that start from automated well tie. Then we will see seismic fault detection and extraction with horizon interpretation, and at the end a quick look of ML on quantitative interpretation as well. So starting from the first step of seismic interpretation, that is seismic well tie, the automated solution enables to estimate single and multi-well wavelets for any seismic data. This approach is designed to support user in seismic well tie scenario when there are a number of wells, so they can increase the efficiency and reduce the expected time by several order of magnitude. It allows rapid screening of seismic well tie quality by initially performing wavelet estimation at each well and selecting the best subset of well for multi-well wavelet estimation. The wells are selected according to automated ranking process, which compute a set of metrics to identify wells revealing poor connection, poor well ties, and requiring more manual investigation, and select the wells according to scoring system. The final objective is to obtain a single wavelet per seismic cube estimated from selected wells. Wavelets are estimated usually from seismic and well reflectivity. The well reflectivity can be calculated via linear Aitken-Richards or nonlinear Zubair equation, and the results of seismic well ties are QC'd using correlation map, well seismic composite, and wavelet statistics as well. So moving towards the interpretation part now. Recent uplift in high performance computing have facilitated the application of deep learning for expensive data set, including 3D seismic large volume as well. Deep learning is its approach for classification and feature extraction from seismic data, especially those that prove challenging for traditional seismic attributes or other deterministic algorithms. This is particularly evident when we are looking on fault detection or horizon interpretation, where deep learning has the capacity to learn complex pattern and relationship. The neural network architecture typically comprises an input layer, hidden layers for computation, and an output layer. AI-based fault delineation technique leverage multi-layered deep convolutional neural network. This CNN convolutional network undergoes training using labeled dataset comprising interpreted faults from diverse seismic data. The network then incorporates positional information from input labels and accesses corresponding seismic dataset to learn pattern. During the training process, CNN updates its layer based on observed correlation, enhancing its ability to recognize fault feature. The architecture often involves an encoder and decoder. Encoder to capture essential features and decoder reconstruct input with focus on fault delineation. So in context of neural network, let's look deeply on this CNN, the encoder and decoder architecture that involves multiple components starting from encoder. In encoders, there are two layers, convolutional and pooling layer. Basically, convolutional layer applies convolutional filter over the seismic to detect and capture feature within the input data. Enable the network to learn hierarchical representation. After convolutional layer, pooling layers has been applied. This reduces the dimensions of feature map produced by convolutional layer, focusing on only most relevant features. After encoder, the next step is decoder. In decoder, the first one is upsampling layer that increases the dimension of feature map, recovering the detail lost during downsampling. The next is transposed convolution, that is inverse of convolution. Expand the feature map and add in reconstructing of input data. Skip connection links corresponding layers between encoder and decoder, allow the network to retain and reuse important features from earlier stages. This enhances the model ability to reconstruct detailed information. So here is the example. The images presented were randomly taken at 3 different epochs during the model training process. At first epoch, nothing has been detected as a predicted fault. By fourth epoch, the model began to exhibit an understanding of faults. And by 19th epoch, it successfully maps the fault with high level of precision. Examining the model performance, the loss function experienced a decrease within initial 5 epochs. And then it stabilizes for approximately next 15 epochs. This rapid reduction in model loss indicates that model quickly grasped the underlying pattern in provided data. The final output that we have is AI confidence cube generated by AI network and serve as a volumetric representation. The data cube encapsulates numerical values that expresses AI confidence in the presence of fault within the input data. The confidence level are quantified in the range from 0 to 100, providing a comprehensive, detailed assessment of AI certainty regarding fault detection throughout the seismic data set. From this AI confidence cube, we can simply extract the fault sticks as that are the fault interpretation. For horizon interpretation, radial basis function and neural network are being used. The architecture of this radial basis function neural network comprises 3 layers. At the outset is the input layer, designed to receive and process extracted seismic feature, serving as initial input for the network. Following this RBF hidden layer, where radial basis function comes into play. This function it's a mathematical function. Transform the input data, map it into higher dimensional feature space. And the last is the output layer. A response that is responsible for generating prediction related to seismic horizon. Let's look at an example in context of deep machine learning based horizon interpretation. In this example, manually picked 29 seed points are taken to initiate the process. Given the limited number of points, less than 100, the initial step involves running the radial basis function. For the model to extend the horizon, the output include RBF attribute that can be used for QC and potential extension of horizon behind the initial run. After RBF, neural network is applied. This generates neural network attribute that user can QC and use for further label extension complementing the RBF attribute. An ML tracker iteration attributes adds in identifying where and when tracking might not have performed optimally, assisting in pinpoint some uncertain areas. This iterative and confidence-driven approach enables user to review, confirm, and discard uncertain areas, contributing to a more robust and reliable horizon interpretation. So from automated well tie, then fault interpretation and horizon interpretation, let's look on ML in seismic inversion. The goal inversion, we need logs. So using this seismic inversion, we can predict missing data if it's present in the logs, integrate both training training data set and inform guidance from geological knowledge in petrophysics and rock physics as well. It's an approach that combines automated machine learning with physics-based methodologies, eliminating the need of parameterization. The final objective is to generate high-quality reservoir properties by quantifying uncertain, ensuring a comprehensive understanding of subsurface conditions. So this we can use for elastic log prediction, petrophysical property cube from seismic inversion output, and fishes cube as well. The algorithm that is used is tree-based algorithm. Is an optimized implementation of multiple additive regression tree gradient boosting algorithm. This algorithm basically utilized for regression problem in machine learning. The technique reconstruct each regression tree iteratively, following a stepwise approach. In each step, a predefined loss function is employed to quantify the error, and correction are made in subsequent steps to minimize this error. The resulting prediction model is essential and ensemble of multiple weaker prediction, collecting, enhancing the overall predictive accuracy. So now moving towards the reservoir modeling part, if we see the traditional reservoir modeling, it faces challenges like handling multiple secondary variables, parameter selections, and demand of interdisciplinary knowledge in geology and mathematics. Our machine learning algorithm present a transformative approach. It provides deeper understanding of geoscience data. In machine learning approach, we can handle non-stationary data without the need of extensive transformation. There is no need of explicit variogram models for our trends. We often require less chanting of parameterization. It can handle multiple diverse geological zones and region, handle multiple inputs, it's more constrained and robust, provide unbiased prediction, and we can access uncertainty. Starting from petrophysical modeling that utilizes upscale well log as training data for machine learning models that are integrated with geostatistical model. We can further input 3D discontinuous or the discrete properties that are extracted as well for the training purpose. This approach is aimed to generate 3D outputs through an estimation workflow providing comprehensive insight in subsurface conditions. This includes generating metrics like mean, median, spread, probabilities, quantiles. Following the estimation phase, the simulation workflow leverage the equal probable stochastic realization derived from conditional distribution. This step results in multiple stochastic simulation, providing a range of possible scenarios that accounts for uncertainties in subsurface properties. And we can also have the option to put the blind wells and then access the uncertainties as well, and with parameters having more impact in this whole modeling workflows. So for fishes modeling, it's almost same. We can employ different machine learning algorithm. We can get different distribution on the basis of algorithms and with rock types as well. By combining machine learning with geostatistical model, it enhances the accuracy and reliability in estimation and simulation workflows. Our 3D output for a holistic view of the subsurface enable more informed decision for reservoir characterization as well. So why we need to integrate AI and expert knowledge? The key to seismic interpretation, the overall workflow, is the interpreter experience and knowledge. So why we need AI? The reality, it should not change anything. So what it does, it introduces new roles and responsibilities. It increases interpreter confidence. And we can facilitate early screening and reconnaissance in various domains of geoscience. It's a collaborative environment where human expertise and AI-driven insight work together to push the boundaries of exploration and advancement of our understanding in the subsurface. There is nothing else why we need to integrate. So the case study that I've taken only the one slide, it's a field, deep water oil and gas from Brazil. It's a complex field where CNN-based technique has been applied as it emerged as a powerful tool for seismic interpretation. One of the key advantages of this CNN lies its ability to operate with limited labeled data, streamline the interpretation process, and alleviate concern related to interpretation biasness. If we have different structured style within the same seismic, we need a separate trained models. There are also a lot of publications available online that have been done through AI/ML, starting from seismic interpretation, then field development planning and uncertainty and optimization. Some are related to machine learning with geostatistical reservoir modeling as well. I'm not going into detail in this slide. These are available online. So the last, what we learned today, the adoption of AI empowers industries and discipline by providing a systematic data-driven approach. It reduces biases, uncertainties, and also guesswork. Its proficiency in unveiling hidden pattern opens up new avenue for exploration and data analysis, ultimately leading to more effective and informed decision. So the last, in conclusion, the integration of AI has potential to catalyze a transformative shift from qualitative to quantitative analysis. This transition signifies a new era marked by heightened accuracy and deeper insights. At the end, integration of AI is not a tool, it's a catalyst in exploration and interpretation. So this is all about today into this presentation. Now the floor is open for question.
Thank you, Mr. Kamran and Mr. Zubair, for the informative presentation. And now we would like to start the Q&A session. If anyone have a question, please feel free to ask by raising your hand or post it in the chat box. And I believe we have one in chat box already. Stating facial modeling is embedded on the same algorithm or only continuous properties.
Sorry, let me go. So can you repeat the question?
It's in the chat box.
Sure, in the chat box it's stating facial modeling is embedded on the same algorithm or only continuous properties.
So fishes modeling is a discrete property that we can take. So algorithm, I don't know which algorithm. If it's referring this algorithm, it's not embedded this with this. It's a separate, you can say, platform, a separate thing for fishes modeling, where we can choose our own model based on specific field or basin, optimize the parameters, and get multiple output each from different algorithm with probabilities of rock types as well. This is how we can quantify the uncertainties in fishes distribution as well.
Thank you. Muhammad, do you have any other question?
Hi, Mr. Kamran.
Hi. Hello.
Yes. My question is about the same tool that we are using. I was just asking if the same tool can be used for the fish modeling, or it's only dedicated right now for the continuous properties like porosity, permeability, and other properties.
So, yeah, Zubair, I think we've already explained this facies modeling. You're asking the same question that, the facies modeling is using the same algorithm or continuous property, right?
No, it's discrete properties. Fishes modeling, you can say it's a discrete. Okay, if you look in detail on back end, you can say it's a continuous, but continuous in a way that it's take the code 1 2 3 0 1 2 3, not like the continuous well log. It takes the code.
Yeah. Because each code represents a different facies.
Yeah, each code represents a different facies. You can take the code.
Yeah, I hope it's clarified. I mean, if you can always reach us through EAGE Kuwait forum or through their email, and you can always contact us back for any other nitty-gritty details or the information, the core information that you are interested in. You can always contact us later.
Anyone have any other questions?
So
okay, I'd like to ask about. Sorry.
Yeah. So if
you have
Shama, I was just thinking that if we have little time, we have one small, a small 2-3 minutes video of showing the the application of AI in fault detection. So, Zubair, do you want to run that quick video?
Okay, let's go to the video. So it's a small video where we have a seismic cube. We just need only a few fault sticks. We can run it. It takes some time and provide the output as a confidence cube. Then we can analyze it with original volume. From this confidence cube, we can extract the fault sticks. It reduces the time to interpret such a multiple fault from, you can say, days or months to hours. Here it just you can extract the point set and then filter the points according to the azimuth and dips and convert it into the fall sticks. The filtering can be also be applied on the fault size as well, the fault point size, and then it's converted to fault sticks and fault framework.
I mean, these algorithms can pick up all the discontinuities, but that is where it is optimizing and improving the efficiency. But at the same time, human intervention, like the expert knowledge, is still required to filter out the unwanted information, and but it has essentially improved the efficiency by, instead of manual interpretation, you're applying these machine learning algorithms to come up with these fault confidence cubes, and then use the other tools to have a proper fault model based on your expert knowledge plus using the AI solutions. So Shama, you were asking a question, probably?
Yes, I'd like to ask about, have you ever had any geological samples like chords and section or even TOC?
Sorry, can you repeat the question?
Have you had any other data from core, for example, or thin section?
Okay, just
using in machine learning and so.
I think, Zubair, I think you did this source rock prediction using this.
Just let me go back. Yeah, this slide.
Using core data and TOC information and all that.
Yeah, let me just give here, instead of fishes prediction here, if we take the example of permeability, we can predict the permeability by selecting train the model for permeability prediction and few wells, and then make the prediction on unseen and new wells, and then compare it with the core permeability. This is one thing. We can quantify our model is working well or not on our prediction. When it's trained, makes the prediction on new wells and then compare it with the core permeability. So specifically, the other thing that we can also use the CSVs, and we can have different and make the prediction. We can even extract data from reports as well using these deep learning algorithms.
I see. Thank you so much. Anyone have another question? It seems that's all. Now, at the end of our session, we'd like to express our gratitude to Mr. Kamran and Mr. Zubair for sharing their knowledge and insight with us. Thank you, Mr. Kamran and Mr. Zubair. Thank you all for joining today. And stay tuned for our upcoming event that will be organized by EAGE, Local Chapter Kuwait, and you can find it in our social media platforms. Thank you all.
Thank you.
Thank you.